Hello, my name is Martin DeKauwe, and Anthony's asked me to talk a little bit about model experiment integration. And instead, I'm going to talk about towards model experiment integration, because I'm going to try to see how far along this path we can actually get. Okay, so this image is taken from a paper in 2019 that kind of aimed to synthesize a whole suite of experiments. You can see over 1,000 experiments. So this is an exhaustive list of every experiment, but it's frankly mind-boggling to think how much work it took to kind of bring all this experimental data together and come up with this synthesis. Okay, so how do we use this then to kind of inform models? And so what they did in this paper was they kind of, what I've shown there in the red box, is they've broken down some of the carbon cycle response variables. This is to do with a water treatment, then they've got increased precipitation treatment, then the interaction of the two. And so this is definitely one way, and you kind of what they were aiming at was trying to understand what the overall responses were of the different variables. And so you can compare a suite of models to that. We can certainly run them. We can kind of look at this on a global sense, but ultimately this will be unsatisfactory. We won't really get anywhere. And this will be because almost certainly there'll be differences between the models and these data, but we won't ever be able to then go back and understand why those differences were. And also it's a challenge to kind of compare directly to these kinds of data sets because it mixes a series of scales, different environments. And so we're left with a real problem here, right? So this is decades worth of investment, over 1,000 experiments, and it's not really clear to us, or not clear to me certainly, and I've been in a group discussion about this before, how do we make use of this data? Because we can't just ignore them, and certainly we've evaluated against some of these data, but it feels a real waste not to be using this data in a more systematic fashion. Okay, so one way to kind of think about model experiment integration would just be evaluation, right? This is typically what happens. And experiments run in isolation. There's a series of hypotheses that are tested here. This is the FACE experiment in the USA. And what they're doing here is they're looking at a CO2 treatment and a warming treatment. And so what happens at some point is a series of modelers come along and they go, okay, these data are great. We should run our models here. And this is what we did in 2017. What I'm showing here is the phenology effectively. So there's a leaf area index varying through time, and you can see that the models disagree with each other. But you can also see that the patterns are quite similar. They've got very smooth shapes. And on the right-hand side, what you can see is saltwater content in blue, and then a greenness index in the green line. And so that's not exactly the same as what the models are predicting for leaf area index, but you can still see a very strong connection between periods where there's apparently soil moisture stress, or certainly a reduction in soil water availability, and a really strong change in the greenness signal. And that's just not picked up here in the models at all. Right. And so this kind of evaluation really shed light on model weaknesses, but only if we've collected all the measurements we need. If there's something missing, we can't then go back and collect them because the experiment's already finished. What we can get from kind of these synthesis or these kind of evaluation things is a better understanding about where our models are at. So in Belinda's paper, she tried to come up with effectively a roadmap of where we were at here. And so the stuff that's shown in the green boxes are things where we are able to use the data to basically discriminate between some of the assumptions in the model. So a series of assumptions in the model, we kind of say, yeah, that one makes sense or that one doesn't. It can also help us identify things that we just think were wrong. So some models made a series of assumptions and we're able to rule them out with the data sets. And that's really powerful because it means we have better models moving forward. But this comes back to this point about, well, we can't go back and take more measurements. It also identifies a series of things where we just need more data, right? The experiments weren't able to tell us, or they weren't exactly the right measurements that allowed us to kind of sense this out in terms of how the models were working. And we do end up with a roadmap when we kind of go for this approach where we've evaluated, and then it's about how we take that moving forward. So I'm going to give you one example of where we've done this. One of the processes we identified as needing more data was trying to understand the sensitivity of transpiration to somatal conductance. And so in a subsequent paper, what we do is we took some FluxNet data and we reasoned that we should be able to work out this sensitivity. And so what I'm showing here is that different plant functional types, so starting at evergreen, needle leaf forest, moving through to crops. And we're looking at basically how coupled leaves are to the boundary layer, so the turbulence around it. And so it kind of, as you move up, it's weaker stomatal control. And so this was something we identified. We then thought about, well, what data can we use to actually look at this? And in some recent work, the Orchidea group have then taken this data and then they're applying this to their model, trying to understand where their model differs from the data and trying to understand the factors that are driving that. And so I think this is really powerful because basically we had a series of experiments. This was never the core aim of those experiments, but it's generated new ideas, new kinds of data-driven work, but also then model work ultimately. And so I think this is a success story of how this work can proceed. Okay, another way to think about this is we can actually use models to make predictions before the experiments start. I'm showing Bill Parton's paper here, and this is again going back to that prairie experiment where I showed the grassland experiment. And what they do in this paper is they're predicting above ground MPP before the experiment starts. And so they've got different treatments here, and they're showing you how the above ground MPP would vary based on different treatments here. And so this is great because it lets you really think about what we think the experiment will do before it's run. The problem with this kind of approach is it's just one model. When we came back and kind of looked at a series of models of this experiment, we see they're all really different. And so in the red box, I've shown the model from the previous one, an updated version of that model. And you can see that had you picked any one of these different models, so this is the responsive MPP in the bars, you may have got a different outcome or may have got a different insight. So these kinds of predictions before experiments are really powerful, but we probably need a suite of models. And that's exactly what we did with the Ute-face experiment. So this is from Belinda's paper. And what we did before the experiment had actually run was we tasked a series of models to make some predictions. And this really shone some important lights on what we thought would happen. So what I'm showing here is the GPP anomaly with time. And we didn't know what the weather was going to be like. So we kind of came up with a theoretical wet period leading to a dry period, then out to a wet period again. And what you can see is that the GPP anomaly is huge in the very dry years. This is in 2016, 2020. And so what we learned from that was that the drought or periods of water stress were going to be really important to what we could learn about the experiments, because the disagreement between the models was far bigger than the response to CO2 in these dry periods. And I guess what this kind of, not that this was a shock, but it really cemented the idea that it would actually matter quite a lot what years the actual experiment ran through. If it was a dry period or if it was a very wet period, how would the CO2 response be different? And so this kind of modeling work can be really good at kind of focusing the mind on what we need to think about in terms of experiments. Okay, so we've kind of done evaluation, we've done predictions before the experiment. So ultimately what we want is this integration. One way to do this integration is we can kind of run the models again, because we ran them before the experiment. And so this is Minkai's new work. And what they've done is they've got a group of phosphorus-enabled models. And now they're basically applying the models back to the experiment. So this is integration in the sense that they made predictions beforehand and now revisiting some of these predictions. The other powerful thing it lets you do is kind of extend the experiment. So the experiment's going to finish at some point, and what they'll be able to do is make predictions into the future. So Anthony Walker had a paper doing this for Duke and Oak Ridge before, and it can be really powerful to look at how the models play out over a longer period of time when you kind of constrain them or you understand them well for the experimental years. Another advantage of experiments in combinations with modeling is if you share your data freely, I'm strongly advocating for that. Well, if you share it freely, what happens is modeling groups will come along and go, hey, we can use these data. We can actually do something different you didn't think about, or that wasn't your intention. So this is from Mongruan's PhD work. And what I'm showing here is the saltwater column at Ute-face and through time. And what she wanted to do was to understand how well cables was simulating these below ground hydrology effectively in the cable land surface model. And you can see that before the cable was really wet. So the blue colors is cable was far too wet. So out of the box, cable was just too wet. And so what she was able to do by using these data was systematically understand all the different things that were contributing to cable's biases here. And in the end, she ends up with an improved performance from the model. It's not perfect, but we really understand what was wrong with the model. But ultimately, this could lead to new things as well, right? At the end of this, you can see that we haven't constrained everything in the model. So we could come up with a series of measurements we think would improve things, or we can identify process that'd be great to have new measurements. And that's where the integration step can come from. Another way to think about integration is to use a formal framework. So we can do data assimilation. So this is from Yichi's group. I'm showing the nitrogen cools for different variables on the left-hand side. And what you can see is the model's making a series of predictions, and it's able to then use those observations to constrain the parameters that made those predictions. This is with the TECO model. And then what we get is we get posteriors for each of the parameters. And this is really important because when we get the very tight PDFs and we understand the model is able to pick out the unique parameters that actually explain the data. But we can also see a series of posteriors that aren't well constrained, and we're not really sure which parameter it is. And what that lets us do basically is say, okay, well, more measurements here would actually tell us something, or we need to understand this process in the model more. And it really makes a strong connection between something that we can tie down and evaluate and actually link that back to data. One problem with this kind of approach is that this data assimilation approach is actually rarely applied in experimental data. And the second thing is that while it can tell us about these posteriors, it may also just reflect weaknesses in the models, or the fact the model's too simplistic. And so it can reflect model structure that's got nothing to do with the experiment in itself. Minkai did a version of this in his 2020 Nature paper. And so this is again nuke face. He's got a very simple model. He's used the data, and what he's trying to do is understand the allocation and turnover fractions to different tissues at the uke face experiment. And then what you can do is you can take that, so those are the gray dots, so the allocation on the top and then turnover, and you can take that and actually, now you've got a data constrained variable that you can then go and use to look at the models. And you can see if you look at the leaf one, it looks like the models were allocating not enough carbon to leaves as the experiment in their predictions before the experiment. So this is a powerful integration between data and modeling by using data assimilation. Okay, so that's kind of still kind of before, or sorry, after the experiments happen. But this is some really interesting work from Yichi's group again. And so what they're doing here is making forecasts. They're ingesting data, these are the red dots, through time, so as they're taken. And then this is from the spruce experiment. They're making a series of predictions for the different treatments through time. And this is a really powerful kind of process, because first of all, it lets you identify weaknesses in the data. So if you've taken some observations, they've got biases, it could be too late once you find out. But because it's ingesting them in a kind of effectively real time, you can kind of see straight away, okay, that doesn't make sense. That's way out of keeping with what the model prediction was or what the past data collection points were. So that can be really powerful for that. But also it lets you kind of make predictions here. You can kind of see what's going to happen over the next year, and you can kind of see what things could be measured. So here you can see that the model's matching data quite well, but we can see what would additional measurements take? What would an increased frequency of measurements take? Or if we could measure that as additional variable, how well could we constrain these predictions? And so this is something quite new, but it's a very powerful way to kind of integrate modeling and experiments. Okay, so in conclusion, I kind of hope I've got across the message. I really think that you can get a lot more success if you involve modeling with the experiments, and that's kind of before it happens. If you can make those predictions beforehand, you can kind of return to them. It really helps you refine data collection, because you can identify the kinds of, not that the model should necessarily drive everything, but you can identify the kinds of things where we don't understand our processes, and that the model just lets us help think about those, I think. We can identify those key uncertainties, and it's not a small step to underestimate this, but once you've set the model up for the experiments, the models are going to come back and run future work here. There's more publications, so I think everyone wins in this kind of route forward. But it remains an open question whether modeling actually ever leads to integration. So in that sense, I've talked about different ways models can integrate with experiments, but integrating in the sense I think I'm trying to get across here means a feedback where the experiment is then does something different because of what we learned from the modeling. And one of the obvious reasons why this absolutely doesn't really happen is that there's never any money for new measurements, right? So I talked about Monguan's work. So if she'd identified a series of things, I said to the face group, could you go and measure this? They almost certainly say they don't have the resources. There's never going to be money for new sensors that we didn't plan for before the experiment. So in that sort of naive version of the world I've just presented, that doesn't happen. Obviously, we have integration because we have future experiments, and we can have some refinement. But ultimately, the challenge is to close this loop, because if we're going to run these models before experiments and we're going to run them during experiments, then we have to make use of them to kind of take different measurements or increase the frequency of measurements. So yeah, that's kind of where I'm at with this. Any questions? And here's the papers I've used in the talk. Thank you.